We are going to start with the fundamental derivation of energy equation, and I am not going to show you all the steps. I will rather tell you the significance of the major steps, and I will skip the rearrangement of terms etc., where no new concepts are involved, but I would simply try to show you that based on a consideration of energy, one would be able to write an energy equation which is a PDE that would take care of the transient effects, the conduction, the convection, and the rate of work done by the system or on the system. So, if we can derive this equation, then based on the application at hand, we will be able to simplify the solution, simplify the equation, and this should give rise to the governing equation for the entire process. And we are also going to check the equation with something that is already known to us. For example, we know that what is the heat conduction equation? The heat conduction equation is simply K del 2 T del x square plus del 2 T del y square plus del 2 T del z square plus Q dot, where Q dot is the heat generated per unit volume, by K. On the other hand side, it should be rho Cp times del T of temperature. So, some of the limiting equations are already known to us. So, you would see that based on the full form of energy equation, if we can impose certain conditions, whether or not we recover the solution, the form which is known to us. But before we go into that part, I would like to introduce a concept which we started discussing about in the last class, which is called the shell balance. Now, this shell balance can be of momentum, it can be of energy, it can also be of a species. So, when we do shell momentum balance, what we do get is a governing equation that describes the velocity, or rather the change in velocity as a function of x, y, z and time. When we write the shell heat balance, we should get what is known as the equation of energy. Similarly, if I write it for a species which is, let us say, reacting with another species in a flowing fluid field, then we would get the species conservation equation, which is going to be very important in mass transfer, but we will not go into that. Let us try to concentrate on how we can write a shell heat balance. The trick is to define a shell of, let us say, some size del x, del y, del z, which is fixed in space. So, a cuboid shape of size del x, del y, del z will have 6 faces, and through these 6 faces, one is the x face, which is perpendicular to the x direction, one is the y face, which is perpendicular to the y direction, and the other is going to be that z face, which is perpendicular to the z direction. Each of these faces will have areas associated with them, and through these areas, heat energy can come into the control volume. So, a control volume is defined by a box of size del x, del y and del z. Through these faces, energy can come into the control volume, into the defined shell, and as a result of which, if the energy which comes in and energy which leaves the system, if they are not balanced, then the internal energy content of the box would increase. Now, when we talk about energy, we are not going to talk only about the internal energy, we also have to consider the kinetic energy. So, a fluid may come through the x phase with certain velocity and therefore certain kinetic energy at a temperature which is different from the temperature of the fluid contained in the box. So, therefore, the entering fluid will have some internal energy and some kinetic energy associated with it. So, it will enter the x phase and will leave the x plus delta x phase. Similarly, it would come through y, leave at y plus delta y, come at z and leave at z plus delta z. So, I would once again show you the way this box is drawn, it is fixed in space, and we would identify the terms which are associated with convection and conduction, and then we'll think of the work done by the system or on the to the surrounding or on the system by the surrounding, and what kind of different work can be done by the system against some forces, which could be a body force or a surface force, as we have discussed in the previous class. But let's once again go through this, which is equation of change for a non-isothermal system. Here I have drawn this box, which is del x, del z and del y. So, these are the x, y and z direction, and the x face, which is this one, is perpendicular to the x this is the x face. The x face is perpendicular to the x direction, and therefore, its area is del y del z. So, its del y times del z would be the area of the x face. Similarly, the y face, which is perpendicular to the y direction, should have area of del x del z, and the z face, which is the front face that you see in this figure, it would have an area of del x times del y. So, fluid enters through x and x, y and z faces, and they leave through the faces at x plus del x, y plus del y and z plus del z. So, this is what we have covered in the last class, and we are going to now write what would be the form of the energy equation for a system of size del x, del y, del z, which is fixed in space, and this is our coordinate system. So, let us see how would the equation of change for a non-isothermal system look like. If I write it in words, then for the volume element, which I have defined as size del x, del y, del z, the rate of accumulation of internal and kinetic energy in the volume element that I have defined, which is del x, del y, del z, the rate is going to be equal to the rate of internal energy I e and kinetic energy K e, which comes into the volume element by convection. So, when there is flow, some amount of energy comes with the flow, and when I talk about energy, I speak about both the internal and the kinetic energy. So, some internal and kinetic energy can come into the control volume, into this volume element by convection, and it is going to go out again by convection from the x plus del x, y plus del y and z plus delta z faces. So, this is the in and the out by convection. If there is a temperature difference which exists in the x direction, let us say I have a temperature difference exists in the x direction. So, then obviously, I am going to have some flow of heat through conduction through this x phase. So, a difference in temperature either in x or in y or in z would give rise to, even if the fluid is still, it would still give rise to conductive heat transfer. So, if there is a temperature difference, there is going to be a conductive heat transfer, and that is what I have written over here is the net. And when I write the word net, what I mean is that it is the summation of energy in and out, in minus out, that I have written separately over here. I have combined them together to write it in the form of net rate of heat addition to the volume element by conduction. So, these two terms are for convection, and together if I combine them and I identify the mechanism by which its heat is going to come into the system by conduction. So, this takes care of all the heat that comes to the system by conduction or by convection. However, there is one missing term that I should take into account at this point, is the rate of work done by the system on the surrounding. And since it is by the system, as a result of doing work by the system on the surrounding, the internal and kinetic energy, the total energy of the system should reduce, should decrease, and that is why we have this minus sign. Had this been a case of work being done on the system, then this sign should be positive. So, based on whether the system does work, in which case the energy content to decrease, energy content of the volume element to decrease, or work is being done on the system, in which case the total energy of the system would increase. So, what I have written over here is nothing but the first law of thermodynamics for and since I am allowing fluid to enter and leave, this must be for an open system. So, the statement which I have written over here is nothing but the first law of thermodynamics for an open system. Now, from this generalized energy equation, one should be able to deduct or to subtract the commonly available equation for kinetic energy of a system, and therefore, what we would left out with is the energy equation where we are only considering internal energy. As a part of the heat transfer course, we are mostly interested in what happens to the internal energy, which is manifested by a change in temperature. So, in order to subtract, in order to take care of the kinetic energy change for this from the more general energy equation that I have written over here, we can subtract the kinetic energy equation in order to obtain purely the energy equation where we are considering only the internal energy. So, that is what we will do next. But first of all, we have to identify what would be the terms for convection, for conduction, and the rate of work done by the system or on the system. So, we will go term by term and see how do they appear in this equation. So, first of all, let us see what is going to be the rate of accumulation of internal energy and kinetic energy within the system, which is defined as del x, del y, del z. So, this must be del t time rate of change of rho times u plus half rho v square, where this u is nothing but the internal energy per unit mass and v is the velocity. So, this u is internal energy per unit mass. So, here I have multiplied it with rho. So, this becomes internal energy, these two terms together they become internal energy per unit volume. So, if it is internal energy, if rho times u has units of, so rho u is internal energy per unit volume. Since my u is internal energy per unit mass, so rho times u is internal energy per unit volume. So, del t of this is the rate of change of internal energy per unit volume. But we would like to, we know what is the volume of it. So, if I would like to find out what is the total rate of accumulation of internal and kinetic energy within xyz, this must be multiplied by del x, del y, del z, which makes it the rate of change of internal energy for a system whose dimensions are del x, del y and del z. As long as my u is defined as internal energy per unit mass, rho is the density. So, therefore, del x, del y, del z times del t of rho u would simply give us the amount, the rate of accumulation of internal energy within del x, del y, del z, and similarly the same logic will also apply to half rho v square. The next one is I am going to write what would be the convection of internal energy and kinetic energy into the element. The element where the element has size del x, del y, del z. So, what is that going to be? Let us pick this figure. In this figure, some amount of this is my x face, which has area of del y and del z. Some amount of fluid is going to enter through this x face, okay. And let us say its velocity with which it comes into this control is del x, del y, del z is Vx, rho u plus half rho v square. This is the internal and kinetic energy. So, what is the fluid mass which enters through this x face per unit time? So, the area of this face is del y del z. So, if this is del y del z, what is the mass that comes in through the x face per unit time? This must be equal to Vx. If you look at the units of these, so this is meter, meter and meter per second. So, the unit turns out to be meter cube per second, which is fine. This is the volumetric flow rate of fluid through the x face. So, this is x face through the x face. So, this is the volumetric flow rate per unit time, volume per unit time. So, through the x face, the amount of volume of fluid which comes in must be equal to del y del z times Vx. This is internal energy per unit mass. This is mass, rho is mass per unit volume. So, what I have then is the product of these two. When I take the product of these two, this is internal energy per unit volume. So, rho times u is internal energy per unit volume, and this term del y del z times Vx, this has units of meter cube per second. So, what I have then here, this term is internal energy per unit volume. So, if I call it term 1, this is internal energy per unit volume, and this one, which if I call it term 2, the term 2 is nothing but volume per unit time. So, the product of del y del z Vx and rho u is simply internal energy per unit time. So, this gives the rate of change of internal energy due to flow of the fluid through the x phase. The same applies for the kinetic energy part of it. So, when you multiply half rho v square with term 2, which is del y del z times Vx, it is going to give you the kinetic energy per unit time. So, together this whole term gives you the, and this is evaluated at x, at this point on this face. So, it comes in through the x face and goes out through the face at x plus del x. So, this is IE and KE in. So, what would be IE and KE out? This must be equal to del y del z as before. This is Vx, but Vx is not at x, but evaluated whatever be the velocity at x plus delta x. So, the entire thing is going to be at x plus delta x times rho u plus half rho v square, all evaluated at x plus delta x. So, the amount of energy, internal and kinetic energy in due to convection. Why due to convection? Because I have a non-zero Vx. Due to convection, would be this term, which I have explained term by term, and the internal and kinetic energy out, which is at x plus delta x, must be everything remaining same except the quantities are now evaluated not at x like this, but is evaluated at x plus delta x. So, when I consider the net, so if I go in minus out by convection, so if I take this, so I am simply going to have del y del z times Vx rho u plus half rho v square evaluated at x minus Vx rho u plus half rho v square evaluated at x plus delta x. So, this is what the expression for in minus out by convection through the x phase would look like. So, I guess this is clear to all of you that how I have arrived at this expression for the convective heat flow through the x phase. Now, I can write the same thing for the y phase. The only thing which will be different here is that y phase has an area equal to del x del z, and since we are talking about y, then the Vx must be replaced with y, Vy, and over here Vx is to be replaced again by Vy. Instead of evaluating it at x, it is going to be evaluated at y and y plus delta y. Similarly, for z phase, this area is going to be del x del y, Vx is to be replaced by Vz, and everything else will remain same. So, in total, to take into account the convective flow of internal and kinetic energy into the volume element del x, del y, del z, I will have 6 terms, 2 terms each for x, y and z phase would give me total of 6 terms that would signify what is the total amount of heat which comes into the system by convection. Similarly, now I am going to write what is so the rate of convection of internal and kinetic energy into the element. There will be total 6 terms as I have explained before, and then we have to think about net rate of heat addition by conduction. I would not say heat here, energy, because I also have the kinetic energy to take care of. Net rate of energy input by conduction, and here I am going to express it in terms of the heat flux. The heat flux in the x direction, the component of heat flux in the x direction. So, this is the heat in per unit area per unit time. So, I must multiply it with the appropriate area. Since it is x phase, this must be equal to delta y delta z. So, this x denotes, it tells me what is the heat that comes to the control volume through the x phase, and the one that goes out through the x plus delta x phase would be this much. So, these two terms together, one at x and one at x plus del x multiplied by delta y delta z, together they tell us about the net rate of heat addition by conduction through the x phase. Similarly, I am going to have the y phase, which will have del x del z the area, and the heat fluxes are going to be q y at y minus q y at y plus delta y, and for the z phase it is going to be del x del y times q z evaluated at z minus q z at z plus delta z. So, these 6 terms, again 6 terms for each of the phases would tell me about the net energy input by conduction. And so, I have taken care of the convection and I have taken care of conduction. So, what is left in my remaining one is, I have already taken care of in by convection, out by convection and net by conduction. So, what is left is work done by the system on the surrounding. So, what is work done by the system on the surrounding? We have to, if we can consider that, then my equation is complete. Now, work done, as we all know, it simply it can be against volumetric forces, that which are acting on the entire volume of the volume element. The common example would be gravity, and the second one is against surface forces, which could be against pressure, which could be against viscous forces. So, these two are again the common examples of surface force, which you can see. So, pressure force and the viscous force. Now, let us see I am not interested in work done, I am interested. So, work done is, we all understand, it's force times distance in the direction of the force So, what would be rate of work done, that is the time rate of work done, it would be force times distance by time. So, distance by time obviously would give you the velocity. So, this is what you are going to get for the rate of work done. So, rate of work done would simply be expressed as, this is time rate of work done, would simply be expressed as force times velocity. So, let us quickly write the expression for the force against gravity forces. So, rate of doing work against gravity would simply be equal to minus, since it's against, work is done against gravity. So, Vx times Gx velocity, and this is acceleration due to gravity, plus Vy Gy plus Vz Gz. So, when you see this equation, you would be able to see that it's the force in the x direction, which is Vx del x del y del z times rho, and this is multiplied by Gx. So, this totally gives you the rho del x del y del z times Gx is the force, because this is mass per unit volume, this is volume, and this is the acceleration. So, this gives you the force, and force multiplied by the velocity in the appropriate direction. So, Vx, Vy and Vz would give you the rate of doing work against gravity. So, again, what is going to be the form for against pressure? It should be the area on which, let us say, the x face del z times P Vx evaluated at x plus delta x minus P Vx at x. So, this is one term plus del x del z P Vy at y plus del y minus P Vy at y. This is going to be the second term plus del x del y PVZ times Z plus del Z minus PVZ. Look at these terms one more time and see what they mean. Pressure is force per unit area. Whatever be the pressure at x plus del x is multiplied by the appropriate area, which is del y del z, to give us the force in the x direction acting on the control volume, acting on the volume element at x plus del x. And we understand that the rate of work done is force times velocity. So, that is why I am multiplying del y del z times p with Vx in order to obtain what is the pressure for what is the work done against pressure forces at x plus del x. And similarly, this is the rate of work done against the forces at x, and I am going to write that for the x face and this is for the z face. So, these 6 terms together would give us the work done against the pressure forces by the volume element del x del y del z. What is remaining here is the work done against viscous forces. Now, work done against viscous forces, this I am going to neglect for the time being, because work done against viscous forces is something similar to solid friction. So, what happens when you work against friction forces? You are pulling an object over a rough surface. So, you have to overcome the viscous forces, overcome the forces, frictional forces exerted by the rough surface on the system that you are pulling over it. So, as a result of which there is going to be heat generation in it, and the energy change, the work that you do, the work that you expend in order to make that block move over a rough surface, it is going to be converted into heat and it will change the energy of the system. Similarly, when fluid flows, especially at high speed through a small duct, there is going to be tremendous velocity gradient which is present. So, let us say I have a jet which is very thin and the fluid is coming at a very high velocity. So, the velocity is large, and if the velocity is large and the gap is small, then the velocity gradient would be very large. And we understand that the viscous force is related to velocity gradient. Okay. The shear stress is mu times velocity gradient. So, if the velocity gradient is large and or the viscosity is large, in that case you will have a strong force that you need to overcome in order to make the fluid flow through that thin conduit at a very high velocity. If that happens, then you do substantial work against the viscous forces. And whenever you do that kind of work against viscous forces, the temperature will increase, and that increase in temperature, which is obtained at the expense of work done by the system, must be taken into account for any energy equation, for any form of energy equation. However, this is only relevant in some special situations. We do not get the heat generation due to viscosity in many of the practical problems. As you would see, it requires high velocity gradient, very high velocity gradient and very high viscosity. So, what are the places in which they become relevant? When a rocket re-enters Earth's atmosphere, its velocity is very large. The atmosphere is still, but the rocket is coming down with a very high velocity. So, near the boundary layer formed close to the rocket, the velocity changes from that of the rocket, which is very large, to velocity equal to 0, which is the velocity of the atmosphere. So, this thinness of the boundary layer and the very high speed of the rocket re-entry would ensure that the frictional heat generated is tremendous, and that is why you would see that the rocket comes as red, almost like a red hot, and there has to be special protective arrangements to ensure that the safety of the astronauts inside the rocket is not compromised. So, that is an extreme example. In some cases, viscous polymer is extruded by making it flow through a very thin gap. If that is the case, then the viscosity is high, the velocity is large, as you would like to have higher throughput of the polymer when you are making a rayon out of it or a sheet out of it. So, the velocity combined with the high viscosity of the polymer and the very high speed with which it comes out of the die ensures that you cannot neglect viscous dissipation. However, in the example that we are going to do in heat transfer, we will neglect viscous heat dissipation. Wherever the viscous heat dissipation is relevant, I will tell you that how to incorporate additional terms into the energy equation, which would take into account viscous heat generation. So, if you look at your textbook and look at the full form of the energy equation, you would see there are a bunch of terms which have mu, which are multiplied with mu, which have mu in front of them. So, the easiest way to identify which term of your energy equation in your text relate to viscous heat generation, look for terms containing mu. If in your problem the viscous heat generation is negligible, drop the entire set of terms containing mu, and what you would have is the energy equation that we are going to use for most of the realistic applications. So, since those terms are complicated, I am dropping them for the time being, but making you aware that in some special situations you need to add them to ensure that your energy equation is complete. So, whatever we have done in today's class, what we will do next is we will add all these terms: the rate of doing work against gravity, the rate of doing works against pressure, the convective terms which are added to the net convective terms, the net energy input by convection, and equate that to the rate of accumulation of internal and kinetic energy within the volume element del x, del y, del z. So, when we write that, what we would and we divide both sides by del x, del y, del z, and take in the limit when del x, del y and del z approach 0, what we would get is we can convert the difference equation, which is a statement of the physics of the problem, into a differential equation that contains, among other things, the velocity due to convection and the temperature. So, we would have to see how we can solve that partial differential equation in order to obtain the temperature distribution. So, that is what we are going to do in the next class. But first of all, we would see whether by neglecting convection are we getting back the equation of conduction with which we are more familiar with at this point of time. So, the beginning of the next class would be to finally get what is the energy equation and try to reduce it, try to simplify it for some applications in which the temperature could be just a function of one variable. It's a steady state and it's a function of x or of y or of z. So, we start with energy equation, see whether it conforms to conduction equations that we are familiar with, and then go into convection. So, that is our plan for the next few classes.